Okay, welcome back. So I left you with this little problem to work out the angular separation between two stars that are 1 parsec apart at a distance of 10 to the 6 parsecs. So you notice here, actually, I haven't bothered converting both of them to meters, as long as both your L and D are in the same units. So here I've left them in parsecs. Then your answer will still come out in radians. If you want to be ultra sure, you can convert everything to meters, of course, by multiplying by 3.1 10 to the 16 on top and bottom, but you can see it's going to cancel out. So that gives you 10 to the minus 6 radians. So again, if we want to convert to arc seconds, we use our old friend here, 206265, to convert to arc seconds. And that gives 0.2 of an arc second as the typical separation between adjacent stars in basically the nearest galaxy. Really. I mean, M31 is about a megaparsec away. Okay, and so you can see that with typical sort of ground-based telescopes, where the seeing the sort of typical image quality is half an arc second or 1 arc second, then you wouldn't resolve the individual stars at all. You just see this sort of sea of starlight, but find it difficult to resolve individual stars. But of course, that all changed, like a lot of things, when we started launching telescopes into space. So the Hubble Space Telescope, which, as you saw from Workshop 1, has a spatial resolution of about 0.05 arc seconds in the optical, is capable of resolving stars in a nearby galaxy. Okay, so let me just show you that. So that here's a little, it's definitely not little, this is a massive mosaic of images from the Hubble Space Telescope. So lots and lots of little tiny images all put together to make a big image of some of the Andromeda Galaxy. And if you follow the link to this site, and I'm going to do it for you now, then you can actually zoom into this image to really see what we're talking about here. Okay, so you can actually see the kind of resolution. So here's that website. So this is a zoomable image. So I'm just going to click zoom, and in we go. Okay, so as we go in, you can see it you can see the individual squares sort of coming into view. Takes a little while to catch up. You can keep going in. Keep going in. Until now we're into this kind of sea of stars here, so now you can start to resolve the individual stars in that galaxy. Okay, so that's the power of that spatial resolution that Hubble telescope delivers. Prior to that, this would just be a blur of starlight, basically. Okay. So next we're going to go on to have a look at a classification scheme for galaxies. So we've kind of looked at this already a little bit, but now we're going to formalize it because this is a kind of a famous diagram here, so-called Hubble's tuning fork diagram. So Hubble is going to a name that's going to feature an awful lot. We've just had him with Hubble Space Telescope. So this is Edwin Hubble, who was doing a huge amount of pioneering work in the field of galaxies, at the beginning of the 1900s, using the sort of big new telescopes in America at the time. And he crops up again and again in this field. So we're going to explore this diagram here. So you can see why it's called a tuning fork diagram, hopefully. It's like the old-fashioned thing now, unless you've been to the doctors and been smacked on the knee by one of these tuning forks to test your reflexes. But it's got that handle and two forks sort of shape here. And you can see that different types of galaxies that we just discussed, ellipticals, spirals, and irregulars, feature in different locations in this diagram. but then there are subclasses in here, and we're going to talk about these subclasses in a moment. So this tuning fork diagram, in a sense, plays a similar role in the field of study of galaxies as the HR diagram does in the study of stars. But there are important differences. I mean, this is not a sort of proper graph or anything. And whereas obviously you can use the HR diagram to sort of track the sort of evolution of stars at different stages of their lives. This tuning fork diagram is not an evolutionary sequence in any shape or form. In fact, if anything, things evolve from right to left rather than from left to right. So it's really just a sort of a memory aid to help people sort of mentally, visually classify the different types of galaxies. So let's go in and talk about these different types of subclasses in turn. So let's deal with the ellipticals first, so that you can see that on that diagram, ellipticals were designated with a capital E, fairly obviously, but that there was also a number following them, an integer number. And that integer number comes from how elliptical the galaxies appear on the sky, okay? So that number is just, again, if you recall, when we were talking about elliptical orbits, we introduced the idea of a major axis and a minor axis. I mean, we were talking about semi-major and semi-minor then, but it doesn't really matter. So where A is the major axis, B is the minor axis. So this sort of ellipticity number for galaxies is given by this expression here, A minus B over A. So this is similar to the eccentricity of an elliptical orbit, but it's different. There's no squares or anything going on here. So it's a different definition. And also the number is always rounded up to the nearest, well, it's multiplied by 10 and then rounded to the nearest integer. So in theory, it's a number between 0 and 10, although again, it never gets near 10. Okay, so that's the theory. And it's important to bear in mind that, this is what we would call the apparent ellipticity of the elliptical galaxy. So it's not usually the true ellipticity of the galaxy, because that's going to depend on our viewing angle, okay? So imagine you could have a very elongated galaxy, but if you turn it around and view it end on, it's going to look circular, okay? So that's where the viewing angle comes in. So it's really just a purely observational quantity. It doesn't really tell us much physically about the galaxy. So here's an example, again, from the universe textbook of 3 different elliptical galaxies with varying degrees of this ellipticity classification. So you can see that, again, if the number is 0, then you're going to have basically a galaxy that looks circular on the sky. And as the number increases, they get gradually more and more elliptical. So again, this number comes from taking the length of the major axis, subtract off the length of the minor axis, and then normalize by dividing by the major axis again, multiplying by 10 and rounded up to the nearest integer. Okay, and that will give you that classification. So you'll get a chance to have a go at this yourself in workshop 4, I think. So next up are the spirals. So these are a little bit more complicated, obviously. So again, they're given a letter to designate them. So capital S is the obvious choice here for spirals. And different spirals are classified by sort of 3 different things that tend to go hand in hand with each other. So the first up is the relative size of the bulge in the middle of the disk compared to the rest of the disk itself. Okay. So what is the relative size of the bulge to the disk? Next up is the amount of sort of dust and gas that appears to be in the spiral galaxy. Okay. And the final one is how tight are these spiral arms wound, if you like. Okay, so are they very tightly wound so that they appear almost circular, or are they quite loose and wind out quite quickly? So there are sort of 3 or 4 subcategories here. Again, I don't want to get too hung up on the terminology here. I'm just going to discuss 3. So there are SA galaxies, so capital S, little a. And again, just keep an eye on the different terminologies here and be careful about them. So SA galaxies, so these are the ones that they've got a large bulge relative to the disk. They have quite tightly wound spiral arms, so nearly circular, and very little gas and dust. Well, not so much gas and dust. Okay. And of course, this goes together because the bulge population does not have any gas and dust associated with it, whereas the disk does. So this really follows from the fact that you've got a large bulge and a smaller disk. Then at the other end of the scale, you've got SC galaxies. So you've got, as we should see, there's A, B, and C. So the SC galaxies are the opposite. So they've got a small bulge relative to a large disk. The spiral arms are quite loosely wound, so they spiral outwards more quickly. And you've got lots of gas and dust because the disk is dominated by gas and dust, as well as the stars, the young stars. And then, of course, you've got the SBs, which are in between these 2 extremes. So SA, B, and C. Okay. So if we just go back to the Hubble diagram for a moment, okay, you can see them here. Okay. And so large bulge relative to the disk, and tightly wound arms. At the other end, a smaller bulge relative to a large disk and loosely wound arms. Okay. And here are some examples, again, in that sort of Hubble sequence, as it's called. So here's an SA galaxy, quite a big bulge there. See the arms hardly spiral out at all, and the disk is relatively small compared to the bulge. If we go to the other end, here you've got a smallish bulge. You see the reddish colors in the center here, and a very large disk. And again, these loose arms that wind out quite quickly. Okay. And this one in between. Okay. Obviously, to really see a lot of these classification criteria, you need to be relatively face-on, or you can't see the pattern of the spiral arms or the size of the bulge relative to the disk. Now, we also have those barred spiral galaxies. Okay, so they're also on the tuning fork. They're the lower fork of the fork. Okay, and they are given the capital letters SB, so capital S, capital B, standing for a barred spiral. And then their classification scheme is basically the same as the normal spirals, going from A to B to C, little a, B, C. Again, this time with the bulge and bar now being dominant in class A. And as you get towards class C, then again, the disk will be much larger relative to the bulge and the bar. And so you can hopefully see some of that. Maybe these aren't the best examples, but so here's an SBA. Okay, so again, a small disk, pretty circular arms, and the bulge and the bar there, sort of dominating the galaxy. Here again, a bit difficult to see the bar in this one, but it's there. Okay, that's an SB little b. And here's this one again. I'm not sure it's the best example really, because it's got a huge bar here really, but the arms are very loose in this one. Okay. Okay. There's another little category of galaxies which are kind of intermediate between the spirals and the ellipticals. So on the tuning fork diagram, these are giving the designation S0. So that's a kind of a hybrid designation. So it's got an S a bit like a spiral, but it's got a 0 a bit like an elliptical number. So they are intermediate in the diagram between the sort of E7s, the most elliptical ellipticals, and the spirals, the sort of the bulge-dominated spirals, if you like, SA or SBAs. So they are literally a hybrid. So they have elements of both spirals and ellipticals in them. So you will see a big elliptical sort of galaxy, but it will have some kind of disk and bulge component in it as well. Okay. They're not going to have much gas or dust in them, and certainly they won't have any obvious spiral arm structure, but there will be some kind of disk-like structure. And they've got another name. They're also referred to as lenticular, which comes from sort of the word for lentil. So they're shaped a bit like a lentil in many cases. So again, that's quite elongated. So again, not as flattened as the disk of a spiral galaxy, but they can be quite elliptical. It's difficult to find nice examples of them. They're a bit of a mishmash of categories. So, so here's one. So again, if you ignore the sort of structure in the middle, you can see that there is a big elliptical concentration of stars here. So that this part of the galaxy looks very much like an elliptical. But you can see a bright bulge in the middle here, which normal elliptical galaxies don't have. They just carry on smoothly increasing to the center. And you can see some kind of remnant disk structure here. It's got striations in it, but they're not proper spiral arms in any shape or form. So there's a little bit of gas and dust left over in a disk in the center here. Okay. So they really are a hybrid of the two. And of course, the irregular galaxies are just lumped in on the diagram at the end there as a kind of an afterthought. They don't have their own sub-classification scheme at all. Okay, so let's just summarize our first foray into the world of galaxies. So we can see that they're classified into these three major groups of spirals, ellipticals, and irregulars. Hubble's tuning fork diagram is a nice way to sort of visualize that detailed classification scheme that we've just outlaid. But as I said before, it's really more of a visual memory aid, and it's not any kind of physical sequence, evolutionary sequence. And something that will inform the sort of next part of our module here is that it is the sort of spiral galaxies and the irregular galaxies that contain the gas and dust and the young blue stars that are recently formed, whilst the ellipticals only contain these sort of old red stars, the red and dead galaxies. And that's kind of where we're going to be going next, really, is to look at this idea of the gas and dust content of stars, of galaxies, and really beginning to look at what we will refer to as the interstellar medium and how that is linked to the formation of new stars. Okay, so that will be the next lecture. But again, just to keep you doing some little calculations and illustrating things to yourself a little bit. One thing I haven't talked about yet is how big a galaxy actually is, sort of physically. So again, here's a nice picture of, this is a bit of a made up picture, I must admit, but this is a real picture of the Andromeda galaxy again. So a nice optical picture here, a nice spiral galaxy, our nearest one. On the same scale is the moon, okay? So the moon, as you learnt in workshop 1, I think, is about, has a angular radius of about ½ degree, I think. Whereas you can see here that if we could actually, well, you can see the Andromeda galaxy with your naked eye if you get on a very dark site and you know where you're looking. Sort of find the square of Pegasus constellation and then go off the tail of Pegasus to Andromeda, and you'll find that it looks very nice in binoculars, but it's actually too big to see with any kind of telescope because it's quite large on the sky. So it's about 3 degrees across here, the diameter. And as I said, it's nearly a megaparsec away, 0.78 of a megaparsec. So again, just do the simple calculation to work out what's the physical dimension, if you like, of the galaxy from this angular size and distance. So for yourself, you can get the measure of a typical size of a galaxy, which we haven't mentioned yet. Okay, so I'll leave it there for now and come back to the interstellar medium next time.